record on this computer. Okay, so we're talking about mini project 4. So in reality, in the real world, if you were doing research, you might pose a question like, what is the average age of a GHC student in fall 2022? Okay, so we pose our research question. You guys are doing, if you're doing the heart disease data set, if you're in healthcare management, you might ask the question, what is the average age of an individual who has heart disease? What is the average resting blood pressure for just, the average person or a person with heart disease? What is, the maximum heart rate when a person is exercising, or, something that would fit with your data. And then what we have based on, our knowledge, our gut, our own personal research. Gosh, you can Google anything these days. We typically pose or propose an answer to the question. So I might say, I believe, if I can spell, the average age of a GHC student in fall 2022 is, let's say, 24. And again, based on my experience, looking at data from previous years, I think that it's 24. Well, then I collect the data, or could be given data, like you've been given data, and I'm going to use that data to test whether my hypothesis is true. So in step 1 of this project, you tell me which variable you're going to do, and then use your research. Again, go out and Google. For example, I went out today just to kind of see, and I could say average age of a person with heart disease. And it tells me that, on average for a heart attack for men is 64.5. For women, it's 70. So your data set has both men and women. So you might, take the average of those two and come up with an answer. It says, your risk for heart disease increases as you go over the age of 65. So maybe you use 65 as your estimate. You might Google the other data set. Supply is a little bit more confusing, but like, what's the average weight of a 20-foot container if they're shipping that stuff on a container? It says it's about 4,914 pounds with a maximum payload. Okay, now the thing you have to be careful about, this measurements in pounds and the measurements in your data set are in kilograms. So you might have to go the extra step and say, okay, well, if you think it's, if you're going to use 48,000 pounds maybe, and we want to know how many kilograms that is, we can look it up. I mean, we can do it. Again, guys, there's so much you can do. I don't have to physically, go to the library, look up in an encyclopedia, or, in some kind of research book. I have Google, or I have different resources. So you can do that. So you have to go out. I do not wish to see everybody making the same hypothesis. That tells me that you guys are probably working together, which is not the intent of the project. Okay, if everybody comes up with the same value over and over again, Ms. Ralston's going to be suspicious. Please do your own work. Okay, so you state your hypothesis. So really what I wrote here in this purpley color should be what you write for question 2. You need to say to Ms. Ralston, I believe the average weight of a shipment is less than a certain amount, or greater than, or is equal, or is not equal. Okay, remember you can use different words. Or I believe the average age of a person with heart disease is whatever, or is greater than. Okay, write it out in words, complete sentence. Then question 3, you convert that to the symbols like we've been using, and then you determine your alternative or vice versa, depending on how you set it up. Step 5, you need to tell me which test you're doing. Are you doing a one mean Z, which should never be the choice? Are you doing a one mean T, or did you choose to do a two mean T? And if you're doing two mean T, you have to tell me, is it paired or independent? You have to identify which of those 4 options you are doing. Again, Ms. Ralston has strongly suggested that you do a one mean hypothesis test. I've also said that none of you know the population standard deviation for any of the variables on either of the data sets, and therefore you should not be doing a Z-test. Okay, then you have to do your mini-tab calculations. And again, record. Guys, record means to write it down. It is not simply copying and pasting the results from mini-tab. Yes, you have to do that, but you also have to write in a sentence. The test statistic is with a p-value of whatever. And then decide whether you reject or fail to reject, and write your conclusion in a complete sentence. Now that was the discussion. We finished up the discussion of one mean or two mean hypothesis test last week. Okay, so you should have all of the information for completing that. I had hoped that you had looked at this document before tonight. Some of you may have. If you have, do you have questions that I can try to address for the whole of the group? Okay, tonight then our plan is to talk about ANOVA, analysis of variance, Kruskal, Walllis, and Tukey's test. This is the last lesson in module 3. Okay, in module 3, quiz 9, which will cover ANOVA with Tukey's test and Kruskal Walllis, is due by Sunday, which is the 30th. Mini project 4 that we just talked about is due on the 31st. Project 5, which deals with ANOVA, analysis of variance, will be due the following Monday, which is November the 7th. Okay, so do you have any questions before we get into the lesson for tonight, general or otherwise? Okay, so you should have found in the course under Module 3 for ANOVA, Kruskal, Walllis, and Tukey's test, I have added updated PowerPoints. There's one for ANOVA with Tukey's test, Kruskal, Walllis, and then the examples are in Word format so that if you chose to print them and take notes on them, you have access to those. Okay, so these are the PowerPoints that I'm going to be using as we go through the lesson. And we're going to start with one-way ANOVA. And which is analysis of variance with a post hoc test called Tukey's. One-way ANOVA is a parametric test. Kruskal, Walllis, which we're going to talk about a little bit later, is a non-parametric test. Okay, so remember we're looking at two different types of test. Parametric test, with parametric test, we typically make about three assumptions. One, we're assuming that we have a normal or an approximately normal distribution. We are assuming that we have equal variances. And the third one's not really an assumption. The third one is that we are looking at a comparison of the means, or a relationship between the means or the averages. Okay, so that's what makes something a parametric test typically, is that we are assuming we're dealing with a normal distribution, we have equal variances, and we are comparing or looking at the means. On the flip side, a non-parametric test, non meaning not, with a non-parametric test, we do not assume that we have a normal distribution. It might be that we don't know what the distribution is. It could be skewed, it could be uniform, it could be some weird shaped distribution. So with the non-parametric test, we don't have to make an assumption about the shape of the distribution, nor do we really have to make an assumption about equal variances. And we look at the relationship of the medians within a non-parametric test. And we're going to look at both tonight. We've done both with the one mean t, or excuse me, yeah, one mean t, two mean t. So we're going to begin with analysis of variance. Analysis of variance is abbreviated as ANOVA. We get AN from the word analysis, O from the word of, and VA from variance. So it's abbreviated ANOVA. We do discuss ANOVA, or one-way ANOVA, in Statistics 1401 or in Stat 1401. So some of this may be familiar to some of you if you've had Stat 1401 recently. Analysis of variance allows us to compare the means of 3 or more populations at one time. We've talked about how to look at the mean. If you have one mean, we had the one mean Z, which is used if we know the population standard deviation. We talked about one mean T, which is used when we do not know the population standard deviation. And so we talked about how to look at that relationship of the mean, whether it's a specific value or if it's less than, greater than, not equal, greater than or equal to. We also looked at how to compare or look at the relationship between two means. We looked at the two mean t-test for independent samples, and we also looked at the paired t-test. Tonight, we're going to look at how we are able to compare 3 or more using analysis of variance. So we could have 3 populations, 4 populations, 5 populations, 10 populations, 20 populations. Okay, we can have, the deal is it's 3 or more. And we get to compare them all at one time instead of having to do individual tests. The idea behind analysis of variance is we're trying to determine if there is a statistically significant difference between the means for each population. Each population would have its own mean, and we're trying to determine if those means are all the same, or is there a difference? But it's more than is there a difference, it's is that difference statistically significant? Are they different enough to conclude that there's something going on? Okay, so we're looking at, and we look at the variation, how different the values are. Okay, that's why it's called analysis of variance. We analyze the variance of each group to look to see if there is that statistically significant difference in the mean. Again, we actually use the variances to determine if the means are equal or not. And one of the ways that we recognize that we're doing analysis of variance involves a quantitative variable. So numbers that are sorted by a qualitative variable. They're sorted into groups by some category. So for example, is there a difference between the mean wait times at 3 different stores? If we looked at, say, the drive-through times at the McDonald's locations in Cartersville, is there a difference between those average wait times? Does a difference exist between the mean number of defective parts produced each day by 3 workers? If you've got 3 employees who are doing the same job, and maybe they're making parts or grinding parts or something, and is there a difference in the number of defective parts? If one of them is creating more defective parts, that's costing the company money. Maybe they need to be retrained. Is there a difference in institutional GPA by major? Okay, so with ANOVA, we still have to make assumptions like we do with any statistical test. There are 5 basic assumptions with ANOVA. First, each population, each group from which a sample is taken is assumed to be normal. So our population from which we're drawing these samples is assumed to be normal. All samples, are randomly selected and independent. Randomly selected means we're using one of those techniques that we talked about earlier. So there's no pattern to it, that every item in the group or every item in the population has a chance to be selected. Independent means that the selection of one item does not affect the selection of the other, of another. Again, we assume that the populations have equal standard deviations or equal variances. Your factor, your X value, if you will, is a categorical qualitative variable. That's the value or the variable that you are sorting by. whether it's major, by workers, by location of the store. The response, the Y value, is a numerical quantitative variable. And it will typically be either at the interval or ratio level. I have to introduce you to a new distribution. To this point, we've looked at the normal distribution and we've looked at the student's T distribution. For ANOVA, the distribution that we use is called the F distribution. It's named after Sir Ronald Fisher, who was an English statistician. That's where the F comes from. Fisher starts with F, so it's called the F distribution. The F test statistic is a ratio. It's actually a fraction. And if you were doing it by hand, it would be very, very messy and would require 5 to 6 preliminary calculations before you ever get to the point, of calculating the actual F test statistic. I'm going to give you a little bit of information about it, just so you don't think it's just waving our hands. But the F test statistic looks at the relationship between the different groups. It looks at the mean from group 1 to group 2 to group 3 to group 4. And that's the value that goes in the numerator, or the top part of the fraction. Then it looks at the mean, or looks at the values within a given group. So it kind of compares all of the values in group 1 to itself. It compares all the values within group 2 to itself, all the values within group 3 to itself, and then gets a value, and that value goes in the denominator, or the bottom of the fraction. Because you have a fraction and you have a numerator and a denominator, you have 2 different degrees of freedom. You have a degree of freedom for the numerator as well as a degree of freedom for the denominator. And just so you'll be aware of the fancy notation, you'll see that fancy notation at the very bottom of this slide. If we have an F distribution with the number of degrees of freedom for the numerator is 4, and the number of degrees of freedom for the denominator is 10, you'll see it written F to identify the distribution. And then you have 2 subscripts. The first subscript is the degree of freedom for the numerator. The second subscript is the degrees of freedom for the denominator. Now, we don't have to worry about determining what those degrees of freedom are, again, because Minitab is going to do it for us. Okay, with ANOVA, again, there's lots and lots of math that's going to go on behind the scenes. Now, again, when I learned this, I had to do it by hand, and you could sit for hours, working through a problem. But Minitab is going to do this work for you, but the information is often organized into a table format. Again, we look at kind of the relationship between the different groups, and we compare it to the differences within the group. Okay, so I'm just trying to show you how it's going to be displayed. We don't really have to worry about all of the different numbers because Minitab is going to do it for us. No researcher in their right mind would try to do this by hand anymore because we have the technology to do it for us. If you really want to understand the theory, I'm happy to explain it to you off camera or off Zoom. I will also tell you, you can actually take an entire course on analysis of variance because there's different types. We're focused on one way, so we're only going to look at kind of one variable, but you could also do two-way ANOVA. You can do what they call multivariable ANOVAs or MANOVAs. So you can actually take an entire 15-week course on analysis of variance. A little bit more about F distribution. The F distribution is not symmetrical. Okay, remember that our normal distribution as well as our student T distribution were bell-shaped, symmetrical, with the mean in the middle. The F distribution is not symmetrical. It is actually skewed to the right. It's actually skewed to the right, where you have lots of data values on the low end and very few on the high end. Because it is skewed to the right, the value of your F test statistic will always be greater or equal to 0. You should never have a negative F test statistic. For each set of degrees of freedom, again, you have a degree of freedom for the numerator, a degree of freedom for the denominator, and you could have those in any combination. Okay, for each set of degrees of freedom, you have a different shaped curve. And I've pulled this graphic where there are a lot of them. The dark blue, you have, with the dark blue, you have 3 degrees of freedom in the numerator and 5 in the denominator. The red one, you have 10 in the numerator and 90 in the denominator. Notice as those degrees of freedom get higher in both cases, this black curve is where you have 50 degrees of freedom in the numerator, 50 degrees of freedom in the denominator. As those degrees of freedom get larger and larger, the curve, the F distribution, begins to be normal. So we've talked about how that the normal distribution can be used to approximate other distributions like the binomial. So the normal distribution can be used to approximate the F distribution at a particular point. At, this particular graphic shows it where your degrees of freedom are 50 in the numerator and 50 in the denominator. So for our hypothesis test for ANOVA, how do we actually write the null hypothesis and the alternative hypothesis? I will tell you that for the null hypothesis will always imply or contain equal in some form. That rule hasn't changed. But really for ANOVA, we only have to worry about the equal option. We don't have to think about less than or greater than or equal to, less than or equal to. The alternative will always be the exact opposite, and therefore it will always be not equal. So again, you don't have to worry about less than, greater than. Your two options are they're either equal or they're not. And what we're looking at is we're trying to say that they're either all equal, or they're all the means are the same, or they're not. And again, there's various ways to say that. Oftentimes for ANOVA, you might see it written in a sentence form using words rather than symbols. We can use symbols, and some researchers prefer the symbols, but you can also write it out in words in sentence form. And we'll talk about that as we go through some examples together. ANOVA allows us to decide if there is a difference between the means. Ultimately, that's what it comes down to. ANOVA is going to tell us, yes, there is a difference, or it's going to tell us, no, there's not a difference. But it doesn't necessarily tell us which one of the groups or which one of the populations are different. That's where the post hoc test, the test that we do after the initial analysis, comes from. And that post hoc test is called Tukey's test. Now, I went ahead and put it here. You always run Tukey's test with a one-way ANOVA. You should never, ever run Tukey's test with a Kruskal Walllis, which is the non-parametric test that we're going to talk about in a little while. But Tukey's test is used after the one-way ANOVA, which again, the ANOVA is going to help us decide, yes, there is a difference, or no, there's not a difference. Tukey's test then is going to begin to look at each pair. It's going to take group 1 and compare it to group 2. It's going to take group 1 and compare to group 3. It's going to take group 2 and compare to group 3. It's going to compare each group to one of the others. But Tukey's test looks at all of those different comparisons at one time. But there is a caveat for using Tukey's test. To use Tukey's test, you have to have the same sample size within each group, meaning you would have to have 5 items in the first group, 5 items in the second group, and 5 in the third group. You could not use Tukey's if you have, say, 7 in group 1, 6 in group 2, and 5 in group 3. The groups are not the same size. If you have that case, it's a totally different test that we're not going to talk about. The Tukey's test looks at a 95% confidence interval for each of those comparisons. And the rule that we use for deciding, is there a statistically significant difference, is whether or not that confidence interval contains 0. If the confidence interval contains 0, then the difference between those two particular values of the mean is statistically significant. Now, again, Minitab is going to do all of those calculations for us, and it actually conducts the one-way ANOVA and will do the Tukey's test with a single command all at the same time. And I have the instructions for that on the next slide in the PowerPoint. So I want us to take a look at some examples. Okay, so this first example says, a regional manager wants to know if there is a difference between the mean amounts of time that customers wait in line at the drive-through window for the 3 stores in her region. She samples the wait times at each store. Determine if there is a difference between the mean wait times for the 3 stores at the 0.05 level of significance. Now I'm going to switch over to my Word document. I have that same question in my Word document. And again, I've told you, and because we're in the section that's discussing ANOVA, you would assume that this is an ANOVA. But I can tell you that on the quiz and on the final exam, you're going to have to identify the fact that you need to use a one-way ANOVA. So a couple of things that I want to point out to you that maybe help you make that decision. First of all, it talks about a difference between the mean. Okay, so the fact that it says mean tells me that I'm going to use a parametric test. And then it talks about the fact that she has 3 stores in her region that she wants to compare. The fact that we're comparing 3 is what draws my mind to ANOVA, because ANOVA, and specifically to a one-way ANOVA, because it is the test that we are discussing that allows us to look at 3 or more groups at one time. One of the other things that you could, but again, oftentimes with ANOVA, your information is displayed, your raw data is given to you in a table or a tabular form. So that may be just looking at how the question is formatted. When I see, oh, I've got a table, that might be ANOVA. It's important when you're looking at these tables that you understand how they're formatted. In this case, the information for store 1 is given on the horizontal. So 2.34, 1.23, 1.89, and so forth correspond to store 1. Okay. Second row, those values correspond to store 2. And third row is store 3. Okay, so you have to understand how to read the table. So those are kind of our clues that we're going to use in ANOVA. One is it talks about the mean. 2, we have 3 groups. And then the fact that my data is displayed in a table is kind of one of those, yeah, that's probably what's going on. It's not the only one that gives it as a table, but it's one of the few that you could consider if when you have a table. But the first step in any hypothesis test is to state the hypotheses. Okay, it's the same step that we've been doing first since we started talking about hypothesis testing. Again, in this scenario with ANOVA, the null hypothesis will always imply equal, and the alternative will always imply not equal. So if I go back up here and I kind of read through my question, it says determine if there is a difference between mean wait times for the 3 stores at the alpha 0.05 level of significance. Furthermore, that statement highlighted in yellow, it says there is a difference. I hope by now when you see the word difference, that means they're not the same, or from a mathematical perspective, they are not equal. And the fact that that is not equal means that that statement highlighted in yellow is the alternative hypothesis. And you can literally write that statement as your alternative hypothesis. So I could literally write, there is a difference between the mean weight times for the 3 stores. That is acceptable way to write the alternative hypothesis for ANOVA. Our null hypothesis then would be, there is not a difference between the mean weight times for the 3 stores. Again, the idea that there's not a difference implies they're the same or equal, which makes it the null. Again, that is perfectly acceptable for an ANOVA to write that sentence out. There are those however, who prefer to write it out in mathematical symbols. Well, again, the idea of an ANOVA is we're comparing the means of the group, each group. So in this case, if we wrote it in symbols, we would say the mean for group 1 is equal to the mean for group 2 is equal to the mean for group 3. We're saying that all 3 of the means are the same, which is what we're trying to verify or prove when we conduct an ANOVA. Now, the alternative is still, even if you write the null in those symbols, the alternative is still in a wordy format. We would say at least. Some text say at least 1. Your text uses the phrase at least 2 of our means differ. If 1 is different, technically there's 2 that are different. So we say at least 2 differs. Now, I have no preference. If I'm not mistaken, the way your homeworks are written in D2L, it uses the words. So for the null, you're going to see the sentence, there is not a difference between the mean wait times for the 3 stores. And the null is going to be, there is a difference between the mean wait times for the 3 stores.
I have a question.
Yes.
So you're saying that for the alternative, that's what the difference is? That there's not an equal sign, but there's 2.
The alternative hypothesis never, ever contains equal. And in this context, the option is that it is not equal. The words in English that imply they are not equal is there is a difference. Is that what you're asking me, John?
What I'm trying to figure out is I'm trying to like wrap my brain around it because it says there's not equal, and then instead for the alternative it says that there is equal.
No, it doesn't.
I mean, there's a difference. I mean, not equal. All right, so all right, you see how the null next to it says equal. So that's what threw me off because you're saying there's not a difference instead of saying that they're all equal
The
at the
English
bottom of that.
words, the English words that are being used to represent equal, which is a math symbol, is there is not a difference. If there is no difference between the items, those items are the same. If they are the same, mathematically, they are equal.
All right, that makes more sense now.
I put the equal and the not equal in front of those to emphasize to you that that's what your statement has to imply. The statement in the null hypothesis has to imply that the items, in this case, the means, are equal. The statement in your alternative has to imply they are not equal. It's the phrase, it's the way the words not equal in this context is being represented by the phrase there is a difference. If there is a difference between the items, they are not the same, which means they are not equal from a mathematical standpoint. And that is always the case. The null hypothesis must always contain equal in some form. If you go back to the normality test, we used the phrase, the data follow a normal distribution. We used the word follow to imply equal because that's the null. And we used the phrase, the data do not follow a normal distribution as the alternative. Does not follow means not, so not equal to a normal distribution. It is all in the verbiage. All right, step 2, in any hypothesis test, not just ANOVA, step 2 in any hypothesis test is to identify the players. And for ANOVA, that means I need the raw data. Okay, I need the data that has been sorted, or if I have raw data, I need to sort it. In this case, it's going to typically be given to you in table form. Again, you want to make sure you know how to read the table. The other piece of information we need is our level of significance, which we're told in the last sentence of the story that the level of significance is 0.05 or 5%, which means my confidence level would be 95%. Remember, your confidence level plus your level of significance must equal 100 or 1 whole. Then step 3 in any hypothesis test is to calculate the test statistic, which for ANOVA is an F, and its p-value. And again, we do not do that by hand. We will use Minitab to perform those calculations. Nobody, no researcher, no statistician in their right mind is going to do those calculations by hand. Now, before we can do the calculations, we have to enter the data. If I already had it in a data set, I could pull the data set in. I don't, so I'm going to have to type the data into Minitab. Now you need to understand how to put it into Minitab correctly. There are two ways to do it. I prefer one way over the other, but I'll show you both and then you can decide for yourself. Okay, we have three different populations. We have information from store 1. We have information from store 2. And we have information from store 3. I'm going to put the information for each store in its own individual column, similar to the way that it's presented in the table. However, the table we talked about gives the data in rows. You always and forever enter the data in Minitab into columns. So I've got to convert the row to a column. So store 1, instead of reading across, when I enter it into Minitab, I'm going to enter it vertically. So I would have 2.34, 1.23, 1.89, 2.31, 3.02, 1.95, 2.45. That is the data that's in row 1 of the table that corresponds to store 1. I've converted the row to a column. The data in Minitab always and forever goes in a column. Store 2, I go back and I enter the information for store 2. Okay, you can see the data on the table. Okay, so there's store 2, and then I come back and I enter the data for store 3. Okay, that is one way to enter the data. I like this way, where you have each one in a column. You can, however, enter it differently. You could enter the wait times in a column and enter the corresponding store number in the adjacent column. So I could have 2.34 corresponds to store 1. I could have 2.87 corresponds to store 2. I could have 1.32 corresponds to store 3. 1.23 corresponds to 1. So I can do kind of like a coding and put all of the times in a single column and then put the corresponding store number in the adjacent column. To me, that gets confusing, so I don't like it that way. But if you prefer that, go for it. You can use that method. Okay, so we have our data entered. You have to have data to do any analysis. So I've entered the wait times for store 1 into its own column, the values for store 2 into its own column, and the values for store 3 into its own column. Then we go to Stat, ANOVA, one way. My data are in a separate column for each level. I have to choose all of the levels. So I have to choose store 1, store 2, store 3. I choose options We always assume equal variances. Make sure the box is checked. My confidence level is 95, and it will always be two-sided. I click OK. We also, again, have it do the Tukey's test at the same time. To get Tukey's test, go to the button that's labeled Comparisons, and we're going to click the box next to Tukey. Everything else stays the same. The only box you check is Tukey's, and you leave everything else alone. And I click OK. And I click OK again. And I'm going to get lots and lots of information. It tells us the method that we used. It tells me what my levels were or what the populations were. I had 3 levels: store 1, store 2, store 3. What we need is the analysis of variance. That was the test we were running. So we need the results for analysis of variance. Again, it comes in a table form. I'm going to copy this over to my paper. What you need from this table is the F value, which is your test statistic, and its corresponding p-value. You have to write them down. Do not simply copy and paste. Every time Miss Ralston works an example, she writes it down. Write it down. So F is 2.29, and the corresponding p-value is 0.129. We'll go back to the Minitab stuff in a minute. Step 4, the same step in every hypothesis test, is to make a decision about whether we're going to reject the null or fail to reject the null. And we make that decision by comparing the p-value to the level of significance. My p-value, which comes from Minitab, is 0.129. The level of significance was 0.05. We make the comparison digit for digit. First digit after the decimal is 1 for the p-value. It is 0 for the level of significance. 1 is greater than 0, so the p-value is greater than the level of significance. When the p-value is greater than the level of significance, we fail to reject the null hypothesis. Step 5 then, which is the same step for any hypothesis test, is to write a conclusion. Okay, let's go back up here and think about what this means. Based on the evidence we have concluded that we are going to fail to reject the null. If you fail to reject the null, that means the null is true or valid based on the evidence you have, and then the alternative is false or invalid. So based on the evidence that we have and the fact that we fail to reject the null, there is not a difference between the mean wait times for the 3 stores. So we're going to write our conclusion. You always include your level of significance at the 0.05 level of significance. There is not a difference in the mean drive through wait times for the 3 stores. Now, the fact that we've concluded there's not a difference, we may or may not normally run a 2-case test. I want to go ahead and run it to demonstrate it for you. Okay, so we've proven there's no difference. We can use the 2-case test to support that belief. So we use the post hoc test to support our conclusion in this case, which is that there's no difference. If there was a difference, the 2-case test would tell us which one or ones were different. The post hoc test is called Tukey's test. Tukey was an individual's name. We actually calculate Tukey's test at the same time that we're running the ANOVA. Okay, so I'm going back to Minitab. If I continue scrolling, we have the model summary. We have the means. Minitab, it wasn't given to us, but Minitab has calculated the means and the standard deviation for each store. Okay, I'm going to keep going. Then you see the header, 2K pairwise comparisons. It gives it to you in a table form, but what we really want to look at is the confidence interval plot, this graph, okay, that compares the confidence intervals all at one time. Okay, so I'm going to paste this. Okay, so 2K's test has compared store 2 to store 1, store 3 to store 1, and store 3 to store 2. Here's how you decide if there is a statistically significant difference. If you go back to the PowerPoint, it said that if the confidence interval does not include 0, then it is statistically significant. There's a statistically significant difference. If you look at this set of confidence intervals, that green dotted line that I just drew in and made darker is the 0 line. All 3 of those confidence intervals contain 0, which supports our contention there is no statistically significant difference in the means. So 2K's test is supporting the fact that there is no statistically significant difference in the means. So again, we concluded there was no difference. The Tukey's test has supported that conclusion. Questions? Okay, I want to look at another example, and hopefully it won't take us as long to go through it. But it says rapid drainage of floodwater is crucial to prevent damage during heavy rains. Several designs for a drainage canal were considered for use in Atlanta. Each design was tested 4 times to determine how long it took to drain the water in the reservoir. Can you conclude that there is a difference in the mean drainage time for the different channel designs? Use alpha equals 0.01. So again, as with any hypothesis test, guys, we start with stating the hypotheses. So if I look at this question, it says, can you conclude there is a difference in the mean drainage times for the different channel designs? Now, first of all, if I'm trying to decide whether, what test am I doing? Am I doing a Z, a T, a two mean T, a paired T, an ANOVA? Again, looking at this problem, first of all, it talks about mean, and it talks about that there were several. It doesn't give a number, but if I look at the table, I can see that there's several corresponds to 5. Well, 5 is more than 2. So again, that is kind of my clue that I'm going to have to do ANOVA because I have more than 2 groups. And we're talking about the mean. It also says in that statement that's highlighted in yellow, there is a difference. In English, the word difference implies that something is not the same. Mathematically, that would mean that it is not equal. And when something is not equal, that makes it the alternative hypothesis. And again, I can use that actual statement as written for my alternative hypothesis. So my alternative hypothesis is there is a difference in the mean drainage times. Let me get some space here. Times for the different channel designs. Again, I copied the sentence that's highlighted in yellow. That is the statement of the alternative hypothesis. That is my alternative hypothesis. That implies that those channel design values are not equal. So when I write the null hypothesis, it has to be worded in such a way that it does imply that they are the same or equal. So I would write, there is no difference in the mean drainage times for the different channel designs. Okay, again, the idea in English would be that no difference implies they're the same, and mathematically that implies they are equal. Step 2 in any hypothesis test is to identify the players or identify the information that you need, which for this problem related to analysis of variance is displayed in table form. Again, it's important to note how the table is set up. Notice that channel 1, the drainage times again are given horizontally. So you have 41.4, 43.4, 50, and 41.2. So the information is in rows. Our significance level is 0.01. That's the last sentence. If alpha is 0.01, my confidence level is 99%. Remember, those have to total to 100%. Third step is to calculate the test statistic, which is F, and its p-value. And again, we're going to do that in Minitab. Now, again, you have to enter the data into Minitab. I'm going to get a new worksheet. Okay, so we have channel 1, channel 2, channel 3, channel 4, and channel 5. And again, when you enter the data, you should enter it in a column. So for channel 1, I would enter the values 41.4, 43.4, 50, and 41.2. And I'm going to do that for each channel. Reading the table that's given to me, I have to read across the rows, but I'm entering it into columns. Whoops. Okay, so I have all the data entered. Then we're going to run our ANOVA. Stat, basic statistics, stat, ANOVA, one way. Again, my responses are in a separate column for each level, and we have 5 of them. 1, 2, 3, 4, 5. My options, again, always assume equal variances. My confidence level this time is 99. It is two-sided. For comparison purposes, I want to use Tukey, which is already indicated. Click OK. I click OK. And again, remember, we get lots and lots of information. My first piece that I need is the analysis of variance results, which is in a table form. Okay, from that table, we need our F value and our P value. You have to write it down. So F is 9.24 and my P value is 0.001. Step 4, as always, we're going to make a decision by comparing the p-value to the level of significance. My p-value is 0.001. My level of significance is 0.01. Again, comparing those digit for digit. The first digit after the decimal in both is a 0. Second digit for the p-value is 0. For the level of significance, it is 1. 0 is less than 1. So P is less than or equal to the level of significance. When P is less than or equal to the level of significance, we reject the null. Step 5, as always, is to write a conclusion. And you need to include your level of significance. So let's go back up here and think about this. If we reject the null, that means the null is false or invalid, and the alternative is true or valid. So based on the evidence that we have in this problem, there is a difference. So we would say at the 0.01 level of significance, there is a difference between the mean drainage times of the different channel designs. Again, the ANOVA has told us there is a difference. It has not told me which of the 5 is different or which ones out of the 5 are different. So again, we run this post hoc test to try to identify which one or ones is or are different. It's still the same test. It's still Tukey's test. but it has a different purpose now because we have proven that there is a difference. Again, we've already run the test. We just got to get the results. So I continue to scroll my mini tab results until I get to the confidence interval graph. And our guideline is if the confidence interval does not contain 0, then there is a statistically significant difference. So if you'll notice on these graphs, this one, which compares channel 3 to channel 1, this one, which compares channel 4 to channel 1, channel 3 to channel 2, channel 4 to channel 2, then you have channel 5 to channel 3, and channel 5 to channel 4. Those 6 do not contain 0. So 3 drains faster than 1 because it's below 0. 4 drains faster than 1. 3 drains faster than 2. 4 drains faster than 2. And looks like 3 and 4 do as well. 5 takes longer because you're up here on the top. But of those, you got 6. The other thing that I can look at, okay, if you look at all those, what you have in common is channel 3 and channel 4. So it looks like channel 3 and channel 4 maybe have a difference. The other thing you can look at is go back and look at the means. If you look at the mean for those different groups, okay, if you go back and look at the mean for those different groups, look, channels 5, 2, and 1 have a mean or an average of roughly 44. Channels 3 and 4 have roughly an average of 30. That's a 14-minute difference, guys. And based on our calculations, that difference is statistically significant. So it appears, based on looking at the comparison for the confidence intervals and then looking at this, that the channel, whoops, let me get a pen. Channel 3 design and channel 4 design drain the flood water faster than the other drainage designs. So if I'm the engineer that's looking into this, I'm going to then do some further research, further testing with channel 3 design and channel 4 design to try to make the best decision. You know, maybe you have to take into consideration, you know, how complicated it is to build the channel 3 design versus the channel 4 design. How much does it cost? And that kind of thing. So he'd have to do further research, but we can tell based on Tukey's test that channel 3 design or channel 4 design are the best 2 options. Questions? Okay, that's ANOVA, which is the parametric test. Again, where you have quantitative data, numbers, sorted into categories. And again, we're making assumptions that we have a normal distribution. We're making assumptions that we have equal variances, and we're dealing with the means. But in some cases, we may not know that we have a normal distribution, or we may not have a normal distribution to start with. It might be skewed or uniform or something else. And so if you have a test where you cannot make the assumption that it is normal and you have equal variances, then we have to resort to the non-parametric test. The non-parametric test, is called Kruskal-Wallis, or it's also called the H test. And it's comparable to the one-way ANOVA, but it's not as powerful because we're not making the assumptions that we normally make. We do not require or have to make the assumption that the distributions are approximately normal or of any kind of particular distribution. And we don't have to make the assumption that the variances are equal. So it's not as powerful a test, but in a pinch, it works. Kruskal-Wallis still allows us to compare 3 or more populations, but it works a little bit differently than ANOVA. Kruskal-Wallis takes all of the data and puts it into kind of one big group, and then it ranks or orders the data. And those ranks actually become the data or the values that are used in the calculation of your H test statistics. And it gives you an approximation of the variation within those ranks. Okay, so it's a little bit different because, again, it's sort of like we didn't talk about Wilcoxon signed rank. I omitted that. It was not on quiz 8, and it's not on the final, so I just went ahead and left it out. But again, it's the idea of you're ranking the data and you're looking at the ranks in terms of your calculations. The H test statistic has a distribution that is approximated by the chi-square distribution. We haven't talked about chi-square yet. We're going to talk about it more in the beginning of Module 4. But the one thing about the approximation is you do have to have at least 5 observations or 5 items per population. So you need 5 items in each group, basically, is what it's saying, in order for this to work. The chi-square distribution is similar to the F distribution that we just talked about, in that it is not symmetric, it is right skewed. Your mean or your average is just to the right of your peak. Typically, your peak would represent your mode. Again, because we are skewed to the right, the value of your test statistic will always be positive or 0. It'll never be negative. And the chi-square distribution is based off of the shape is determined by the number of groups or the number of categories that you have. And so the shape is determined by the degree of freedom. The degree of freedom is the number of groups minus 1. And as your degrees of freedom get higher and higher, when they get to about 90 or a little bit beyond 90, the chi-square distribution can be approximated using the normal distribution, as is the case with a lot of distributions. So some assumptions that we make with Kruskal-Wallis: our dependent variable or your output, your y's, are typically going to be numbers, but they're numbers that can be ordered. So they're at the ordinal or the continuous level such that they can be ranked. The independent or the X value consists of 3 or more categorical or independent groups. Again, they're independent in that one doesn't affect the other. There's no overlap in the groups. Your observations are also independent. What you observe for one group does not affect what you observe for the other group, or even within the group. What happens on the first observation doesn't affect the second or the third. And the fourth assumption is that the distribution of scores for each group of the independent variable, we kind of assume they have the same shape. And that doesn't mean they all have to be normal. We're really assuming they're not normal, but they have the same shape. Maybe they're all skewed to the right, or they're all skewed to the left, or there's some kind of weird combination. Again, for our purposes in this course, to make the determination whether you're going to use Kruskal Walllis or whether you're going to use ANOVA, if you know that the distributions are normal, we're going to do one-way ANOVA. If you know that the distributions are not normal, we're going to use Kruskal Walllis. And again, I'll reiterate, you never, ever use Tukey's test with a Kruskal Walllis. The hypotheses are pretty much worded the same way as we had with ANOVA, but instead of addressing the means for Kruskal Walllis, we think and compare the medians. We're looking at the medians. So we're going to be thinking about that all of the medians are the same. There's no difference in the medians between the groups. That would be your null because there's no difference, implying equal. Or you have your alternative, which would be that they are different or they're not the same. And that would be your alternative. Again, we're looking at the relationship of the medians with Kruskal Walllis. Okay, so initially, when you're looking at these problems, you may have to decide, well, should I do one-way ANOVA or Kruskal Walllis? Again, for our purposes, if it's normal, you're going to do ANOVA. If they're not normal, you're going to use Kruskal Walllis. If you're uncertain or you're not told, then you may have to decide for yourself. And we can decide whether something is normal or not, one, by comparing the mean and the median, or we can look at the box plots, and we can look at multiple box plots side by side. And then as we need to, we'll conduct the Kruskal-Wallис hypothesis test. Okay, so on the next slide, I give you the Minitab instructions for looking at the box plots and calculating the descriptive statistics if you need to decide whether or not the distributions are normal or not. Then on the next slide, I have the instructions for the Kruskal-Wallis. Again, it is a non-parametric test. Okay, and then I have an example. Okay, so I want us to take a look at this example before we go tonight. I've got about 20 minutes, I think. So I'm going back to my paper where I have my example. Now, again, I've told you here in this problem that it's the Kruskal-Wallis, but let's talk about how we know that it needs to be a Kruskal-Wallis. So it says, a meteorologist wishes to see if there is a difference in the number of deaths in the United States due to severe weather. The data from the past 6 years are shown here. At a 0.05 level of significance, is there a difference in the number of deaths from the different weather conditions? Well, one of the things that jumps out at me almost immediately after reading that problem is there's no mention of mean. If you go back and look at those problems related to one-way ANOVA, it said, is there a difference in the mean number of things? So there's no mention of mean. It doesn't indicate how many groups we have here, but it does say different weather conditions. And I can tell from my table here that I have 4 different options. So I have 4 groups or 4 populations, which is more than 2. So again, that leads me to, I could do ANOVA. It doesn't tell me here that we have normal distributions. So probably the first thing that I want to do is to maybe think about or investigate the distribution. I'm still thinking in my mind that I want to do either one-way ANOVA or a Kruskal Wallis. So I can investigate the distributions, or I could say, well, they didn't tell me it was normal. I'm not going to make that assumption, so I'm going to automatically do Kruskal Wallis. Because unless I'm willing to make the assumption that it's normal, then I can't use one-way ANOVA. But I want us to look at how to investigate the distributions. Now, there is a big difference in how you enter this data into Minitab for Kruskal Wallis. For Kruskal Wallis, you have to enter all of your quantitative data in a single column and code it. So in this case, I would have to put the number of deaths in column 1, and I'm going to have to put the severe weather, the category, in the column next to it. You kind of have to use that coding system. You cannot do Kruskal Wallis by putting it in individual columns. You have to do a single column. Okay, so for example, again, lightning is given to me vertically, so I would enter my values for lightning. Gotta make sure I can read it. 39, 41, 73, 74, 67, and 68. And so I may go back and put lightning, 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 lightning. Okay. And then I can go back and enter the next data. 30, 39, 39, 53, 50, and 32. Oh, come on. 53, 50, and 30, 32. Those are due to a tornado, so I would label them as tornado. Whoops, only if Miss Ralston can spell. Okay, then I go back and I enter the ones for flash flood. Okay, and then I do the ones for blizzard. Okay, so you have to enter them this way, guys. You have to put all of your quantitative data in a column and code in the adjacent column. And again, I'm trying to investigate my distribution. So I'm going to do a box plot. So I go to graph, box plot, and I want to look at all four of them at the same time. So I'm going to do multiple Y's, categorical variables, and you have the instructions in the PowerPoint. My output is my number of deaths. They're sorted by severe weather. And I click OK. And it creates, and I'm going to copy it where we can see it. It creates a box plot for each category. You have blizzard, flash flood, lightning, and tornado. Now remember, to be normal, your box is supposed to be kind of in the middle of the whiskers. It looks like maybe blizzard might be normal, but flash flood is certainly not. I don't believe lightning is, because look at how the median is kind of way out of whack. Tornado, maybe. If you don't like looking at pictures, you're not visual, you can look at the numbers. I can have Minitab calculate the descriptive statistics for each category. I can sort by the weather, and I only really need to look at the mean and the median. Remember, we learned early on for comparing distributions, if the mean and the median are approximately the same, they're symmetric. If they're not, then they're probably skewed. So if I look here, it looks like blizzard, the mean and the median are roughly 45. So that is probably normal. But if I look at flash flood, there's a difference there, a pretty big difference. Same thing with lightning. So I know that those two are skewed. So all of the distributions are not the same. I cannot assume that they're normal. So that leads me to, I've got to do Kruskal Wallis. Okay, so I'm going to begin. I've got to do Kruskal Wallis. Because my distributions are not normal. I cannot make that assumption. We begin, as we always do, and we state the hypotheses. You have the null, and you have the alternative. If I go back to my story, it says, is there a difference in the number of deaths from the different weather conditions? Again, it has the word difference. Difference in English means they are not the same. Mathematically, that would mean they are not equal. And if they're not equal, that means that statement is the alternative. And again, I can use that same statement almost. We need to add one word. Okay, so we would say there is a difference in the median number of deaths in the U.S. due to severe weather. Okay, we're saying there's a difference, but we're looking at the difference in the median. So you want to put in that word. The null would be there is no difference in the median number of deaths in the U.S. due to severe weather. Step 2, in the hypothesis testing process, is to identify the players. Again, the players are your data. Okay. And you need your alpha, which is the significance level is 0.05. So my confidence level is 95%. We've actually already entered the data into Minitab, but you have to enter it the same way as I did before. Step 3 is to calculate the test statistic, which is H, and its p-value. And again, we are not doing that by hand. We will use Minitab. So again, to do Kruskal Wallis, we've already entered the data where we have the number of deaths in a single column and its code in the adjacent column. That's the way the data has to be entered. We go to Stat, Non-Parametrics, Kruskal Wallis. My response is the number, which is the number of deaths. The factor is the categories, which is severe weather. We click OK. And again, we get lots of data or lots of information. What we need is the test. Okay, so I have my test results. Notice that on this table, on the test results, you have not adjusted for ties and you have adjusted for ties. We will always read not adjusted for ties. That allows for the fact that there could have been a tie between the ranks. Okay, we are not worried about the adjustment. Again, we write down our test statistic. My H test statistic is 5.54. My corresponding p-value is 0.136. Step 4, same as always, make a decision. We make a decision by comparing the p-value to the level of significance. My p-value is 0.136. My level of significance was 0.05. Compare it digit for digit. 1 compared to 0. 1 is greater than 0, so P is greater than the level of significance. If P is greater than the level of significance, we fail to reject the null. Step 5, write a conclusion. Going back to our hypotheses, we came to the conclusion based on our evidence that we are going to fail to reject the null, okay, which means the null is true or valid, and the alternative is false or invalid. So I'm going to write my conclusion. At the 0.05 level of significance, there is no difference in the median number of deaths in the United States due to different severe weather events. And I made it with 4 minutes to spare. Guys, you're basically doing the same process over and over and over and over. What's changing is which test you are doing. You're going to have to be able to identify which test you need to do when you take the final exam. So all these little tidbits that Miss Ralston is telling you, you need to try to make yourself a list. Okay, so that finishes our discussion of ANOVA with Tukey's test and Kruskal Wallis, which also finishes Module 3. You have Quiz 9, which is over ANOVA with Tukey's test and Kruskal Wallis, due on Sunday, which is the 30th. Mini Project 4, which is the 1 mean or 2 mean test, hypothesis test, is due on Monday the 31st. Mini Project 5, which is actually over ANOVA, okay, is due on the 7th of November. Okay, so you need to look ahead, guys, and start thinking about how you can sort your data, how you can take a column with numbers and sort it by a column of words within your data set. And if you've read the information that Miss Ralston has in D2L, she gives you some hints on that. If you haven't taken the time to read the information on your data set, you might want to take that time to do so. Okay, so do you have questions before we end tonight's session?
No, it's okay. I was just trying to listen to everything. So.
Anybody else have questions? All right, guys, if not, then I will see you next Tuesday and we will start Module 4. We will start Module 4.